Good day, students. Welcome to the next topic of our General Maths Unit 2 unit. This is on networks, and you'll be working on this for the remainder of this semester. Now, before we start this lesson, I encourage you guys to watch this video that I've linked in here. Sort of gives you a good insight as to how networks work, although it doesn't fully encompass everything there is to know about networks. Okay, but it's just a good video to watch as an introduction to this topic. Okay, so just you can click on that link, or you can play it from our browser in our OneNote. Just a heads up, I don't want to hear anybody asking me, sir, what questions do we need to do? It is going to be in the first page of these notes. I've also made a checklist for you guys here. It's exactly the same one. Okay, so just look in our OneNote. It's all there. Okay, but you'll be working through these exercises for the remainder of the term. And let's get to it. So this new topic is called networks. Okay, now I've talked about this before, and you have done a bit of this in your matrices. Okay, but here we'll go into a bit more depth into what it is and its applications. Okay, so networks. Some things that we'll cover, and these will be each exercise. So today we're just going to look at basic features of graphs. We'll look into the rest of these as we go. Alright, so we're going to skip 9a because we don't really need it. The video that I asked you to watch just before is sort of similar to 9a, so we'll just go straight to 9b. Definition of a network graph. A graph, also called a network, consists of two components, your vertices and your edges. Now, you'll see this when we worked with matrices, and I did mention these two words before, vertices and edge. Vertices are represented by dots, edges are represented by lines or curves with vertices at the endpoints. The shape and length of the curve is irrelevant. Okay, so basically all you need to know is that a vertex, plural for it is vertice, okay, they are dots. Okay, so for example, here I've got, we'll make it 4 dots. Okay, because I feel like it. 4 dots, and these are called vertices. The edges, we call them, okay, are the lines. So they can look like any sort of thing you want them to in terms of where they're connected. And they are basically what connects the vertices together. Okay, so the vertices are the dots, or you could call it a vertex. Okay, vertice is plural for vertex, so vertices would be obviously more than one vertex. Okay, they're all the same thing. One is just vertices just means more than one, and the lines, we refer to them as edges. Sometimes you'll hear me call them lines and dots. Okay, just know what they are. Okay, the lines are your edges. They are what connect the vertices, and your vertices are the dots. So this is an example of a network graph, and you will have seen this with our matrices. So what are the applications? So given in a set of objects, graphs can be used to represent which pairs of objects have or do not have some kind of relationship or connection with one another. For example, in a group of people, which pairs are Facebook friends? So if, say, for example, you have 10 friends like Mr. Torre has on Facebook. Out of those 10 friends, let's say there's 10 people. Is that 10? 1, 2, 3, 4, 5, 10. Okay. Which of them are connected by friends? So this guy could be friends with that person. That person could be that person there, connected to those people. This person could be connected to that person. That person could be connected to there, that to there, that person to that person to that, and that person to that. See? These are people who are friends with a certain person. And this is Mr. Torio. So he's actually not friends with any of them. Haha, okay. It could be, okay, in a group of cities which pairs are directly connected by a railway. So you could have, like, say, for example, a bunch of cities, another city here, maybe another city over here. Okay, where are the railways connected? Maybe there's a railway that connects from this city, let's call this city A, B, C, and D. Okay, there's a railway that connects to city B. City B has a railway that goes to all of them. Okay, or city B is able to connect to all of them. Meanwhile, maybe city C has a connection with city A as well. And the only way to get to city D is everyone has to go to B first. Okay, that's another example. A collection of websites which could be paired directly to hyperlinks. So that's for the IT people there. And or in a molecule, which atoms are directly connected by chemical bonds. So let's say you have, okay, H and H. What's this? H2O. I don't know. Actually, I actually don't know if that's how water looks like. But here's a network graph of possibly how water looks like. 2 hydrogen atoms and 1 oxygen atom. I'm not a chemistry teacher, so I wouldn't know if that was what it looks like, but that's an example of it. Okay, and that's how we represent different connections using network graphs. So basic features of other features of a graph. So we know about your edges. We know about our vertices. So edges are your lines, vertices are your dots. But we've also seen this before, a loop. So basically a loop is a type of edge that joins a vertex to itself. So here's an example of a loop. There's my vertex, and a loop could be something like that. We've seen loops before, okay, in matrices, where that means that they connect to themselves. Okay, so that's one term of what a loop is. There. The degree of a vertex is the number of times it is the endpoint of an edge. Basically what this is saying is the degree of a vertex is the number of lines that are connected to it. Okay. A normal edge contributes to 1 degree of a vertex. A loop, which is an edge that joins to itself, so a vertex, that joins to itself, contributes to 2 degrees of a vertex. Now, complicated, I know, but we will go through what that means in a second. I'm just going to read the rest of this. A vertex is called odd or even, respectively, if its degrees is odd or even. So remember, degree refers to how many lines or how many edges connect to that vertex. Okay. Normally, a normal edge, say for example, I want to draw another vertex here and a edge. This edge, this vertex has a degree of 1, okay, because there's only 1 line connected to it. Whereas this vertex has a degree of 3, okay, because there are 3 lines that connect to it. This is 1 right there, 2 is another one, and then 3 going the other way. Okay, and we'll go through that in more detail in these examples here. So for each of the following graphs, find the degree of each vertex, and in B, state which vertices are odd. So let's actually, before we, what I like to do with these sort of questions is I like to label each of the vertices. So you're going to label these. If you have your notes, I know some of you, actually no one will have the notes here, but watch over these notes or look through these notes again. I'll make sure that these notes are printed for you when we get back from lockdown. So this is vertex A, B, C, D, and E. It's important that you actually use some sort of naming convention to name your graph, so your vertices, just so you know what's what. So for A, so this is how we write the degrees for our vertices. So for A, we're going to write degree. For A, remember degree refers to how many lines connect to that vertex. So the degree for A, deg A is, we've got 1, 2, 3. 3. The degree for B is equal to 1, 2, 3. Just 3 for B. The degree for C is equal to 1, 2. Okay. The degree for D, is going to be 1, 2, 3, 4, okay, and then 5, okay, because the loops count for 2 degrees. So there's 5 degrees for B, and then the degree for E is going to be 1, 2, 3. Okay, pretty straightforward. So in terms of which vertices are odd, you've got vertex A, vertex B, vertex D, and vertex E are odd vertices. Cool. Let's look at the second one. Again, label your vertices so you know what you're working with. So that's A, B, C. Okay, so let's do this. So the degree for A is equal to 1, 2, 3, 4. Okay, because the loop, remember, counts for 2. That's 4. Degree for B is going to be 1, 2, 3. Okay, 3. Degree for C, you've got 1, 2, 3. Okay, so that means the odd vertices are B and C are odd vertices. Cool. Last one. This one's a tricky one. Okay, so let's write this down. You've got A, B, C, D, and E. Okay, so let's write all the degrees for them. Degree for A. Okay, I can see that there's no lines connected to it, so it'd be 0. Degree for B is going to be 1, 2, 3. Okay, so 3. Remember the loops count for 2. Degree for C is going to be 1, 2. Degree for D, sorry, it's going to be 1. I can just see the one line going down. Degree for E is going to be 1, 2. Okay, 2. Okay, so now stating which degrees are odd, I would say the only one odd here is B. So B is an odd vertex. Okay, but what about the other ones? Okay, I know C and E we can discount because they're even, but A and D, well, if we look at A, there's nothing. Okay, it's a 0, so you wouldn't really include that whether it's odd or even. So you'd say A has a degree of 0, and D has a connection of 1, or a degree of 1, which means it's a prime number, so it's neither odd or even. Okay, so the only odd one there would be B. But you would state that A and D, so A has 0, D has 1, but you can leave it at that. All right, the handshake theorem. So these two statements, two equivalent statements, meaning these two statements are equal to each other. So the sum of the degrees, so if you were to add up all the degrees here for any graph, okay, is going to be equal to double the number of edges. So double the number of edges, meaning if you were to add, if you're trying to find the total degree for all of this, so if you wanted a shortcut for adding all of this, basically, all you got to do is count the number of edges. So 1, 2, 3, 4, 5, 6, 7, 8, and then double it. And then that should give you the total number of degrees. So according to this, there's 8 edges. So that means the total degree is 16. And if you add this up, 3 plus 3 plus 2 plus 5 plus 3, so that's 6, 8 plus 5 is 13, plus 3 is 16. So that makes sense. All right, so this statement is saying the sum of the number of degrees, so if you wanted to add all of the degrees in a graph, okay, is equal to double the number of edges. And every graph has an even number of odd degree vertices. Okay, this is saying that every graph will have an even number of odd degree vertices. So if you look at, I just repeated that, but if you look at the number of odd degrees here, there are 4. So that's an even number of odd degrees, or an even number of the number of odd. So there's 4. Here you've got an even number again of odd degrees. Okay. If an edge connects two distinct vertices, it contributes to one to the degree of each of the vertices. Hence, it contributes to 2 to the sum of degrees for all vertices. So what that's saying is, say you got two vertices, okay, and this is just your graph, and it's connected by an edge. This counts for a degree of 2, okay, because if that's A, that's B. All right, so if you do degree of A, that equals 1. Degree of B, that equals 1 as well. The total degree for this is 2 for this graph. Total degree. Right, so what that's saying is, I'll that out. Actually, I'll leave that there. What that's saying is each line or each vertex edge contributes to 2 degrees. Okay, a loop will contribute to 2 degrees of its vertex. Okay, and it's the same thing. So let's say you got a loop. Let's say this is my graph. Okay, and this is the edge. Okay, graph A, sorry, let's call that A. The degree of A would be 2. Okay, so every loop counts for 2. Okay, to its degree, to the degree of that vertex. All right, let's do some examples. Find the number of edges for each of the following graphs. All right, so find the number of edges. Oh, sorry. Actually, we don't even need to. It's just asking us for finding the number of edges. And then from there, we can also find the total number of degrees. So in this graph, I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, because I've got 8, and notice how I mark them out. Okay, that does help with counting how many edges there are. Okay, so there's 8, so that means the total degree should be 16. Okay, because it's double the number of edges. So I'll count again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, for this next one, finding the total number of edges will give us the total number of degrees. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there should be 11 here. So if there's 11, that means the total degree should be 22 because there's 11 edges. Okay, I'll double count that just to make sure I didn't miss anything. But you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I think it's 11. I think that's the trickiest part with networks is sometimes people do miss lines and edges and vertices. You just got to make sure you count them properly. That's it for this chapter. All right, so go ahead and do the exercises for chapter 9b, which will be in your exercise books. So 9b, questions 1, 2, and 4. Thank you.